Physics Part 237. Consider an isolated spherical conductor connected to a high voltage supply. It is found that as the potential of the sphere is increased, the charge stored on the sphere also increases. The graph showing the variation of charge on the conductor with potential is shown in the figure. It can be seen that charge Q is related to potential V by Q relative to V. Hence Q is equal to C into V, where C is a constant which depends on the size of the conductor. C is known as the capacitance of the conductor. Capacitance is the ratio of charge to potential for a conductor. C is equal to Q over V. Another chance for confusion. The letter C is used as an abbreviation for the unit of charge. The column is an italic letter C. It is used as the symbol for capacitance. The unit of capacitance is farad, symbol F. 1 farad is 1 coulomb per volt. The farad is an inconveniently large unit. In electronic circuits, laboratory experiments, the range of useful values of capacitance is from about 10's power raised to minus 12 farad. A picofarad, or 1 pf, to 10's power raised to 3 farad, 1 millifarad, or 1 mf. For a list of decimal multiples and submultiples used for the units. Circuit components which store charge and therefore have capacitance are called capacitors. Example, calculate the charge stored on an isolated conductor of capacitance 470 farad when it is at a potential of 20 voltage. Using C is equal to Q over V, we have Q is equal to CV is equal to 470 into 10's power raised to minus 6 into 20, which is equal to 9.4 into 10's power raised to minus 3 C. Now it's your turn. The charge on a certain isolated conductor is 2.5 into 10's power raised to 2 C when this potential is 25 volt. Calculate the capacitance. Energy stored in capacitor. When charging the capacitor, work done by the battery to move charge onto the capacitor, energy is transferred from the power supply and is stored as electrical potential energy in the capacitor. The camera flash units use a capacitor to store energy. The capacitor takes a few seconds to charge when connected to the battery on the camera. Then the energy is discharged very rapidly when the capacitor is connected to the flash bulb to give a short but intense flash. Since Q is equal to CV, the charge stored on a capacitor is directly proportional to its potential. From the definition of the potential, the work done and therefore the energy transferred is the product of the potential and the charge. That is, W and EP is equal to VQ. However, while more and more charge is transferred to the capacitor, the potential difference is increasing. Suppose the potential is V0, and when the charge stored is Q0, when a further small amount of charge, delta Q, is supplied, the energy transferred is given by delta EP is equal to V0 into delta Q, which is equal to the area of the shaded strip in the figure.